All right, so let's continue talking about double integrals. Now, sometimes a region is going to be better described in polar coordinates than in rectangular coordinates. And so we're going to look at how we're going to set up a double integral in polar coordinates. Remember, if we're making a conversion from rectangular to polar coordinates, we have a few relationships that are going to be helpful. The first is r squared equals, well, let's just remind you what the difference is, right? So if you have some point x, y in rectangular coordinates, where you have x is how far you are along the x-axis, and y is how far you are along the y-axis. In polar coordinates, we give it r and theta, where r is how far you are from the origin, like that's the distance you are from the origin, and then theta is the angle from the x-axis. So some conversions that are going to be useful are r squared equals x squared plus y squared. Also, if you want to convert from well, actually, also the theta is going to be the, I guess the tangent of theta is going to be y over x. That's a useful conversion sometimes. X would be r cos theta, and y is r sine theta. So these are going to be useful for converting your function of x and y into a function of r and theta. Okay, so it's worth thinking about what a polar coordinate rectangle actually looks like. So if you're going from let's see, from R1 to R2, and say we have a couple different thetas, theta 1, theta 2. So this is what a rectangle would look like. This is what the rectangle R is all points r theta, such that r1 bounds r and theta 1 bounds theta. Okay, so with rectangles looking like this, it's worth thinking about what the differential kind of area of one of is going to be. Now, if we were to slice this up into little pieces, okay, so this is what you should have in mind as this thing gets sliced up. Okay, so if we're going if theta is going from theta 1 to theta 2, going from r1 to r2, oops. What's the area of this little segment? Well, you could think of it in terms of the difference in a circle. Pi times r2 squared minus pi r1 squared, that would be the area of a ring, right? But I don't want the whole ring, I want a portion of the ring. And so what I would be taking theta 2 minus theta 1 over 2 pi, because that's how many radians there are in a circle. So this is going to be my delta A, my area of this little section. The idea is we want to think about this distance here is my delta R, and the difference, or I should say, my delta R is R2 minus R1, and my delta theta is my theta 2 minus theta 1. So what we want to do is think of the limit of this thing as delta R approaches, dr, and delta theta approaches d theta. What happens when these two things get closer and closer to each other? So in the limit, well, what we want to do is actually clean this up a tad, because you can see that there's, we have, say, theta 2 minus theta 1 actually can be written simply as delta theta over 2. The pi, I'm going to cancel with the other, the pi's would be canceling. And I can factor r2 squared minus r1 squared as r2 minus r1 times r2 plus r1. All right, now this is actually delta theta over 2 times delta r, because that's what r2 minus r1 is. And in the limit, r2 minus r1 as oh, sorry, this is a plus. As r2 minus r1 goes to 0, right? That means those are both converging. Those are both converging to r. That's going to converge to r plus r. So this is going to converge to d theta times dr times 2r, and then it's divided by 2. So, so dA is going to be r dr d theta. This is the area of this like differential little segment in polar coordinates. And this is going to be super important. All right, so then this is how we set up a double integral in polar coordinates. So if f is some continuous function on a polar rectangle r given by these bounds, r is bounded from a to b, positive numbers a to b, and theta is bounded from alpha to beta, and we're assuming the difference between beta and alpha is somewhere between 0 and 2 pi. So the double integral over r is going to be the integral from alpha to beta, the integral from a to b, f of r cosine theta, r sine theta. So this is our conversion of x and y, right? And then dA is going to be r dr d theta. All right, so let's take a look at this double integral. This is over the region R, 3x plus 4y squared. R is a region in the upper half of the xy plane bounded by circle x squared plus y squared equals 1 and x squared plus y squared equals 4. So you can see the region that we're integrating is this area here. So we're going to set this thing up in polar coordinates, obviously. Okay, so the our alpha, like the lower bound, we have alpha equals 0 and beta equals pi. Those are like the angle bounds that we're going to be observing. And then we have the smaller radius is going to be the radius of 1, and the outer radius is going to be radius, oops, that's a 2. Okay, now what is the function going to look like? Well, it's going to be 3 r cos theta plus 4 times r sine theta squared, which is 3r cos theta plus 4r squared sine squared theta. Our integral becomes integral from 0 to pi, integral from 1 to 2, 3r cos theta plus 4r squared sine squared theta, r dr d theta. So actually what's better is if I actually distribute that r. I'm going to take the integral with respect to r first. So this is actually going to be, we're going to have an r, this is actually r squared and r cubed. Okay, so the integral from 0 to pi, we're going to have 3, this is 3r squared, and that's 4r cubed. Well, that's nice because we just get r cubed times the cosine theta plus r to the 4th sine squared theta, and integrating from 0 to 2 d theta. Okay, so we've got, let's see, we're at when r is 2, we're going to have 8 cos theta plus 16 sine squared theta minus 8 sine cos theta minus 16, sorry, minus cos theta minus sine squared theta. Okay, this is going to be, I forgot this whole part, 0 to pi d theta. We'll clean that up a little bit, of course. So this is actually going to be the integral from 0 to pi of cos theta 8 minus the 7 cos theta plus 15 sine squared theta d theta. Now, one thing that is interesting about this is that the sine squared, the cosine is going to be whatever, yeah. Okay, so the integral of sine squared is a little bit messy unless you realize that you can use a double angle formula. The power reduction formula on the sine. And to remind you that the sine squared of theta comes out to be 1/2 1 minus the cosine of 2 theta. And so that's exactly what we're going to do. We're going to write this as the integral from 0 to pi, 7 cos theta plus 15 over 2 times 1 minus the cosine of 2 theta, d theta. This is actually not so bad to take the integral of. The thing about the cosine, though, is the cosine function, if you think about going from 0 to pi, the cosine goes like this, right? And so whatever is positive counteracts with what's negative. And so the cosine is not going to give you anything. In fact, that's the same when you're going from 0 to pi or 0 to 2 pi. So this is in fact, so what I'm trying to say is the cosine portion of these is actually going to have an integral of 0 because that we're going from 0 to pi. The cosine theta is going to be 0 in integral. The cosine of 2 theta is going to go from, well, theta would be going, the 2 theta is going from 0 to 2 pi, and that's going to be 0. And so what we get in the end is just going to be 15 over 2. Sorry, where's that pi? Oh, sorry, 15 over 2 times pi. There's the pi. That's the area of this thing, 15 pi over 2. Okay, now let's find a volume of a solid bounded by z equals 0 and z equals 1 minus x squared minus y squared. You should have in mind that this thing is a paraboloid, so what we're looking at is this kind of a thing. This doesn't look very much like a paraboloid. It looks like a hemisphere, but it's not a hemisphere, it's a paraboloid. The key thing to think about is like what's going to be the intersection of this thing with the xy plane. And realize when you plug z equals 0, you're going to get x squared plus y squared equals 1. So this is just going to be an integral over this region that's a circle of radius 1. And the angle is going to go from 0 to 2 pi. 0 to 2 pi. And the radius is going to go from 0 to 1. And I'll put my r dr d theta over here because I'm going to need that. Now I want to just express this in terms of the polar coordinates. Remember this conversion, x squared plus y squared is r squared. So this is actually going to be 1 minus r squared. And when you write it like this, this is almost laughably easy. So this is going to be the integral from 0 to 2 pi. So this is r minus r to the third, right? Because we distribute this r to both terms. So we're going to have 1/2 r squared minus 1/4 r to the fourth, integral from 0 to 1, and then we have a d theta still hanging around, ready to go. We're going to, we can actually, actually we evaluate this thing, 0 to 2 pi. Let's just do this. When we plug in 1, we're going to get 1/2 minus 1/4, and that's simply going to be 1/4. And because there's no thetas in this, when you integrate from 0 to 2 pi, you're just going to get 2 pi over 4, and that's pi over 2. One thing I could also make use of is when you're doing these integrals, because my function didn't have any thetas in it, I can actually separate it. And this is something that you can do as long as your bounds don't depend on the other variable. You can factor your integral into the two parts. But anyway, we'll talk about that in class. Okay, so now we're going to extend this to having variable bounds. So this is the equivalent of a general polar region. If we'll consider just where the bounds on the angle theta are constant bounds, alpha and beta, but the radius is going to be bounded by a function of theta. So if the radius r is bounded between h1 of theta and h2 of theta, you can just set up the integral just like this, where you have the bounds h1 of theta down here and h2 of theta up top, and we're going to evaluate the integral just like we would have with rectangular coordinates. Except remember, you can't get away from that r. r dr d theta. Never forget, r dr d theta. Let's look at an example using this. All right, we're going to find the volume of a solid that lies under a paraboloid z equals x squared plus y squared, above the xy plane, and inside a cylinder x squared plus y squared equals 2xy. Now that is an elliptical cylinder, mind you, and let's just see what what looks like on the intersection on the xy plane. I don't know why I said it's an elliptical cylinder. It's a circular cylinder. If we centered this thing, this is actually x minus 1 squared plus y squared equals 0, or sorry, equals 1. So this is a circle of radius 1 that's centered over here. Now, if we were to, so this is the idea. We want to take this region here, and we're going to take the different angles. You see here as we slice this up with different angles, the radius is going to depend on theta, and the distance is going to be found based on if we convert the equation of the cylinder into polar coordinates. X squared plus y squared is r squared, and 2x is 2r cosine theta. Notice there's an r on both sides. R is always positive, so I'm going to divide by r. I'm going to get r equals 2 cos theta. So this is the equation. I'm going to have my radius is going to be between, my r value is going to be between 2 cos theta and 0. And theta is going to range from what? Theta is going to go from here all the way up to here. That's where my thetas are going to go. I'm only going to be going from negative pi over 2 up to pi over 2. The xy plane is my lower bound. My upper bound is this paraboloid, And notice this is a nice little paraboloid because z equals x squared plus y squared is just the equation z equals r squared. So here's my integral. My angles are going to go from negative pi over 2 to pi over 2. My r is going to go from 0 to 2 cos theta. My function is r squared, r dr d theta. That's my dA. So this is r cubed, right? Negative pi over 2 to pi over 2, 0 to 2 cos theta, r cubed, dr d theta. Let's take the integral. So we're going to get the negative pi over 2 to pi over 2 doesn't change. What we're going to have now is going to be 1/4 r to the 4th, going from 0 to 2 cos theta and a d theta. The nice thing about this is that when you plug in 0, it's just 0. So I'm going to put this in. Is negative pi over 2 to pi over 2. We have, let's see, we got 2 cosine theta. That's going to be 2 to the 4th. That's a 16 divided by 4. That's 4 cosine to the 4th theta, d theta. The cosine function is an even function, and so as such it's symmetric. So actually we can just take this as 2 times, so if we factor if we took the 4 out, we'd have a 4, but then it'd be 4 times 2, which is 8 times the integral from 0 to pi over 2 of cosine to the 4th theta d theta. Remember what we would do for things like this? We're going to need to, let's see, what do we do? We're going to have to do power reduction rule for this bad boy. That one's going to take another page, so I'm going to move on to the other page with this integral. For power reduction, the cosine squared of the angle can be written as, what is it? It's 1 plus, or it's this. It's 1/2 times 1 plus the cosine of 2 theta. So I'm going to actually have, right, this is 8 halves. Let's say a half times a half, that's a 4th. So that's actually going to be well, I guess I'll do it and I'll do all of the steps. 0 to pi over 2. We're going to have 1/4 1 plus cosine 2 theta squared d theta. The 4th comes out, so actually I'm going to have 2 integral of 0 to pi over 2, and then we're going to have, let's see, what do we have? We have 1 plus 2 cosine 2 theta plus cosine squared of 2 theta. In order to take this integral, we're going to unfortunately need to once again do a power reduction rule. And this is going to, the cosine squared of 2 theta is going to become 1/2 times 1 plus the cosine of 4 theta. That's 2, 0 to pi over 2, 1 plus 2 cos 2 theta plus 1/2 times 1 plus the cosine of 4 theta. And then everything d theta. All right. Well, okay. Well, I'm gonna just clean this up a teeny tiny bit more. So it's going to be 2 times the integral. I can do it in a few different integrals. The integral from 0 to pi over 2 of 1 plus 1/2. That's 3 halves. d theta plus the integral from 0 to pi over 2 of 2 cosine of 2 theta d theta plus the integral from 0 to pi over 2 of the cosine of, sorry, that's 1/2 the cosine of 4 theta d theta. The one nice thing that I get out of this is the cosine of 4 theta is going to be the cosine going from 0 all the way up to 2 pi. And the integral of that is going to be 0. So this whole thing is going to be gone. What I'm left with then is this integral 0 to pi over 2 of, and of course, this here just comes out to be 3 pi over 4. And so the integral of 2 cosine 2 theta is, I want to be a little bit careful. If I let u be 2 theta, then du is going to be 2 d theta, which I have there. And so I'm going to write this as, now the bounds are going to be, so let's see, it's going to be, this is 2 times 3 pi over 4 plus the integral. The lower bound is still 0, but the upper bound, u is 2 theta, so the bound in terms of u is going to be pi. And I don't even know why I'm bothering this, because the cosine from 0, the cosine of I should have realized this earlier on, right? The cosine function, when the argument goes from 0 to pi, it's going to cancel out with itself. That's actually gone. So what we're left with in the end is just 3 pi over 2. Yes, yes. Just to illustrate what I was talking about here. Right, here's the cosine function. This is pi, and if we're going to continue another to 2 pi, you can see that the plus and the minus cancel, the minus and the plus, right? So that's why these integrals are both 0, because 4 theta, when theta goes from 0 to pi over 2, that actually goes from 0 to 2 pi. Okay, hope that that's clear enough. We'll go over more of these examples in class. We'll get some more practice, and you'll become polar coordinate integral experts. All right. Bye.